Hello, we're back and we're going to do the same thing except for instead of going to B or to 5, we're going to some B. Okay, so I'm just going to do the whole thing again. I know it takes forever. So we're going to split this into n intervals. So each one will have a width of b over n. First one will be right at b over n. The second one will be at b2b over n, 3b over n, etc. So I can say then that the area, and I'm going to do approximately again, we'll take the limit later. The area is approximately b over n times the summation from I equals 1 to n of f of b times I over n, right? So this b over n, remember, is the width of each interval. We're going to multiply the height of the rectangle by its width for each one. I equals 1, we have b over n. We evaluate it at f, we get this height, we multiply by b over n. I equals 2, we have 2b over n. We stick it into the function f of x equals x, we get the height, and then we multiply it by b over n to find the width of that rectangle, and so on, and so on, and so forth. So, I'm going to take and put bi over n into the function, and I get bi over n. Just as I did last time, I can pull this b over n out because b is just a number and n is just a number. So we have b squared over, we have b squared over n squared times the summation from I equals 1 to n of I, but we can write that as b squared times n squared times n plus 1 over 2. And then we can write that as b squared n squared over 2n squared plus b squared n over 2n squared. And right here you can see that these n's are going to cancel with themselves. And we can say that the area then, since the area is approximately this, we're going to say the area is equal to the limit as n goes to infinity of b squared, these n's have canceled, b squared over 2 plus b squared over 2n. When we let n get really large, this term goes to 0, and the area is precisely b squared over 2. Okay? Ooh, let's make it even a little more sophisticated here. And let's add a in here. And let's find the area in this region. Well, if we were to do this whole process again, from 0 to a, adding up the area of all these little rectangles, which I will call this, remember, so this is a little change in x, I'm going to call it dx. This is a little change in y, I'm going to call it dy. Right? We're taking all these little changes in x's and y's, and we're multiplying them together and adding up that area. And if I do that from here to here, versus from here to here, I'm going to get the same thing, except for my b squared is going to be an a squared. So the area here, under the curve, area under f of x equal to x from a to b is going to be, we're going to take this part out, this b squared over 2, that's this whole area, and then we're going to subtract out this piece. So we have b squared over 2 minus a squared over 2. Okay, and that will be the area. Okay? And now I want you to recall this. We've started looking at integrals, right? And this is called an indefinite integral. And when you took the indefinite integral of x dx, you got x squared over 2 plus c, right? And, oh, wow, something's happening here, huh? So, what we need to think about now is what is going on here, and what is the relation between integration, or I'll say between differentiation and integration. And specifically, how does this integration relate to area? Right? And this is where Newton and Leibniz and another fellow that I can't remember the name of, this is where they start finding areas, these areas under the curves, and they notice that the numbers they're getting are very similar to integrals, right? So our question now is, how are integrals related to area, and how is differentiation related to integration? We might suspect that differentiation and integration are inverses of each other already, right? Because if you take the integral of x squared dx, you will get x cubed over 3 plus some constant. But of course, if you turn around and take the derivative of x squared over 3 plus c, you will get back where you started, right? So they definitely, integration and derivation are inverses of each other in this sense. But how does this relate to slope and area? How are these things related? And that's what we're going to explore in the next video.